Hello everyone. Welcome to the ILTA Physics problem solving session. Today we are going to work through some problems related to the Atwood machine. The Atwood machine, as shown in the diagram below, is a famous device that connects objects to both sides of a pulley to experimentally prove Newton's laws of motion. Since this device can directly demonstrate the theoretical principles of classical mechanics, it is a very common topic that frequently appears on physics exams. What's interesting is that the analysis of the object's motion changes depending on whether we treat the pulley, which changes the direction of the force, as an ideal model or as a real-world model with its own mass and size. We'll start by summarizing the problem types for these two pulley models, and then solve a problem applied to actual rotational motion together. The Atwood machine is a pulley device designed in 1784 by British mathematician George Atwood to experimentally verify Newton's second law of motion. As you can see in the diagram, two objects are hung on either side of the pulley, and the relationship between velocity and acceleration of the objects moving due to gravity was proven through experiments. First, let's analyze the motion of the objects assuming an ideal pulley that only changes the direction of the force. Regardless of the pulley model, the analysis of the Atwood machine works like this. First, if we draw a free body diagram for block 1 on the right, the weight due to gravity acts downward, and the tension of the string acts upward. The difference between these two forces is the net force acting on the block 1, which, according to Newton's second law, equals the product of mass and acceleration. If this explanation isn't quite clear yet, I recommend checking out the Related My Theory lecture first. In the same way, for block 2 on the left, the difference between the downward weight and the upward tension equals the product of that object's mass and acceleration. There are two things you need to be careful about here. First, since the two objects are connected by a string and move together, their accelerations have the same magnitude. Second, because of the difference in mass, the lighter object moves up while the heavier object moves down, meaning their accelerations are in opposite directions. Therefore, in our case, the acceleration of block 2 will have a downward or negative direction. Now, let's integrate the pulley model into these equations of motion. The ideal pulley model assumes that the pulley has no mass and that there is no friction involved in its movement. The no mass assumption is key here. Because the pulley has no mass, it has no rotational inertia while it rotates. And since there is no rotational inertia, no torque is required to make this pulley rotate. This means that the two tensions acting on the right and left sides remain exactly the same without any loss, because no torque is needed to turn the pulley. In other words, the tension T1 equals the tension T2. To put it another way, an ideal pulley only serves to change the direction of the force and doesn't affect the motion of the objects at all. So, if we organize the equations using the free body diagrams for each block and the condition that the two tensions are equal, we can find the acceleration of the objects as follows. In the case of an ideal pulley model, the acceleration of the connected objects is calculated with the difference in the two masses times the acceleration due to gravity in the numerator, and the sum of the two masses in the denominator. Now on the next page, let's analyze the case where the pulley model considers actual mass and size. Now for the exact same Atwood machine, let's analyze the motion where the pulley has real mass and size. To give you a hint in advance, since we are adding the rotational motion of the pulley to our analysis, the two tensions created by the hanging objects will not be equal, as some torque is needed to rotate the massive pulley. Alright, let's look at this step by step. Just like the analysis of the ideal Atwood machine, the equations of motion for the two blocks hanging on each side are exactly the same. The difference here is that since the pulley has mass, it requires torque to make it rotate. We will analyze this rotational motion of the pulley from both a kinetics and kinematics perspective. From a kinetics perspective, the torque on the pulley is calculated as the product of the difference in tension between the two sides of the string and the distance from the axis of rotation. Also, from a kinematics perspective, the torque of the pulley can be calculated as the product of the rotational inertia of the disc or cylinder and its angular acceleration. Here, the rotational inertia of the disc is calculated using the following formula, and the angular acceleration is the linear acceleration in the tangential direction divided by the radius. If we solve these equations for the acceleration of the objects, you'll notice that the mass of the pulley is added to the denominator of the acceleration formula we derived earlier. Intuitively, since some force is lost to make the pulley rotate, we can mathematically confirm that the acceleration is slower than it would be with an ideal pulley. For a more detailed breakdown of Atwood machine motion, please make sure to refer to the related theory lecture. Now, with these theoretical concepts in mind, let's solve some related pulley problems. Problem 51 is an Atwood machine type problem, but instead of masses on either side, it gives us the direct pulling forces as conditions. Since the objects themselves aren't given, we aren't looking for linear acceleration of an object. Instead, the question asks for the angular acceleration of the pulley itself. First, since the mass and size of the pulley are provided, we can apply the massive pulley model to find its rotational inertia. According to the formula, the rotational inertia based on the disk model is 0.036 kilograms meter squared. Now, let's use the forces applied to the right and left sides of the pulley to calculate the torque in each direction. First, the torque from the 12 Newton force on the left acts counterclockwise, and as the product of the radius and force, it equals 3.6 Newton meters. The torque from the 10 Newton force on the right acts clockwise, which is minus 3.0 Newton meters. Make sure you clearly understand the signs for clockwise and counterclockwise directions here. Therefore, the net torque acting on the pulley is 0.6 Newton meters in the counterclockwise direction. You can also think of this by calculating the difference between the left and right forces from the start, which results in a net torque as if only a 2 Newton force were acting counterclockwise. Whichever way you calculate it, once you have the torque, you can plug it into the relationship between rotational inertia and angular acceleration to get 16.67 radians per second squared. Problem 56 is a classic Atwood machine problem involving a pulley with mass. According to the problem description, 1.5 kilograms and 2.5 kilograms blocks are hanging on each side, and while the pulley has no friction, it has a diameter of 30 centimeters and a mass of 0.75 kilograms, is asking for the acceleration of the lighter 1.5 kilograms block. First, for a pulley with mass, the rotational inertia based on the disk model is 0.00844 kilograms meter squared. Now, as we summarized before, if we set up the equations of motion for each block and include the torque for the pulley's rotation, the acceleration of the objects is organized as follows. If we plug the given values into this formula, the acceleration of the two objects is 2.24 meters per second squared. Since the calculated acceleration is positive, we can see that the lighter 1.5 kilograms block moves upward at an acceleration of 2.24 meters per second squared. That's it for today's lecture. You all did a great job. See you next time.